Hello, welcome to the Caramel webinar here in Barcelona in the IoT Solutions World Congress, where we have here some booth to demonstrate all the technology produced by this project, a research and innovation project funded by the European Commission. 15 partners we are working from Europe and 3 for Korea. The idea for this project is that you imagine that you are inside your connected autonomous car and some cyber attack appear, like the traffic sign is modified or you are receiving a GPS signal that is not in the correct way. But here our projects try to solve these kind of things, to be that this mobility in the SICAM environment will be secure. Okay, and for this project, we divide this project in 4 pillars. The first pillars that we work on is basically to go with the cyber threats of perception layer. The second pillar that we work on basically is that all the cyber threats that are impacting in the telecommunications layer. The third pillar that will be presented today is about how the cyber threats impact in the electric car and for instance, the charging stations. And the last pillar that was covered by the Korean partners in this project is about the remote control vehicle cyber threats. And after this introduction, we will see the different pillars in actions here in the fair.
Hey everyone, my name is Wael from Capgemini, and we're excited today to be here in the IoTS to showcase or to share what we did in Caramel. So to do so, what we want to show in this section of the video is our GPS spoofing attack, obviously to try to avoid it, and our sign tampering solution. How it works? So just imagine, as a driver, getting able to get a notification about a tempered sign, or maybe getting a notification about an upcoming tempered sign. How we do this? Simple. So for the first one, it's on device, it recognizes a tempered sign and notifies you directly that you are seeing a tempered sign. Indeed, you're seeing a tempered sign. And for the upcoming signs, so we rely on our backend solution, what we call a backend solution. So basically, our different cars embedded with the solution can directly communicate to the backend solution and send the signal there via a protected protocol that we developed in this project. And then we increase the level, we increase the urgency level and the dangerous level, and that way we can notify other cars as well that you will have a sign, that you will have a trigger thing there. This backend solution as well serves for other pillars, serves for other users in this model and in this project that we developed together that you will see up next.
Okay, so hello all. I'm glad to welcome you here in the Caramel booth. I am Petros Kapsalas. I am the technical leader of the ADAS team for Panasonic Automotive Europe. And as Panasonic Automotive Europe, we are leading the Pillar 1 activities for Caramel EU project. As it regards to the Pillar 1, it is the pillar which attempts to propose solutions regarding the detection and the mitigation of cyber attacks on the perception layer of the autonomous vehicle. So the main aim of this pillar is to make the software which does the scene interpretation immune to cyber attacks. And we have considered 3 different layers of cyber attacks in Pillar 1. The first layer is the physical layer. So the assumption there is that a malicious user intervenes in the structuring element of the scene by disturbing the visual appearance of some traffic elements like the traffic signs. Now the software which has been developed performs at first the autonomous car detects that there is a traffic sign, and then the cyber security detection and mitigation engine developed in Caramel will detect that this traffic sign has been attacked by a malicious user, and the attack will be mitigated using some machine learning techniques. The idea is that once the attack is detected, then the mitigation engine tries to revert the attack, and if the attack is not reverted, then the backend part of Caramel is being activated in order to assign all the control to the driver. Apart from the physical layer of the attack, we are also considering the sensor layer, where a malicious user remotely intervenes to the sensors of the autonomous vehicle. For Caramel, we have engaged an autonomous car which is equipped with multiple sensors, like an array of sonars in the front of the car, and also a front camera, and front and rear camera, and also mirror cameras, in order to guarantee a 360 degrees of freedom surround view system that monitors what happens around the vehicle. And apart from the cameras and the sonars, we are also using a Velodyne Lidar on the top of the car, and a GPS in the back of the car as sensors that give you a holistic understanding of the scene. So, in the second layer of attacks that we are investigating in Pillar 1 of Caramel, we assume a remote user which activates some malicious software that intervenes to the quality of the signal captured by the sensors. So it can be a malicious user that introduces noise to the camera signal or to the Lidar signal, or performs some GPS spoofing. And in Caramel, we have developed some detection and mitigation engines, which at first detects that a malicious attack has been performed on the sensor, and then the attack is mitigated using some deep learning techniques or some variational techniques on the sensor layer, which remove the attack without affecting the edge content of the image, that is very important for all the recognition tasks. Also in Caramel, we have produced, we are trying to use the redundancy of the sensors, like the Lidar and the camera, as one of the main tools to revert the cyber attacks. So there is a component which has been implemented within Caramel that is called holistic situational awareness, and it tries to mitigate the cyber attack introduced in the camera by using the scene understanding modules developed for the Lidar sensor, and vice versa. So, for example, if somebody has performed an adversarial attacks on the neural networks running on the vision perception system, and some objects are not visible anymore, then the perception modules running on Lidar will contribute these objects in the map, and so the overall scene understanding will not be distorted, and as a result, the safety level that we produce from this project is not going to be deteriorated. Another type of attack that we are considering in Caramel is the GPS spoofing attack, and during this attack, a malicious user attacks to the GPS. It distorts the location as it is understood by the GPS. So it gives you wrong information about the coordinates where the vehicle is located within the city. And again, we have developed some machine learning techniques in order to detect and mitigate the attack. And this solution is cloud-based. So once the coordinate within the city where the attack has been performed were identified, then these coordinates are communicated to the cloud, and all the other users are aware that on this specific location of the city, it's very possible to be attacked in your GPS sensor. We have used multiple integration surfaces in order to integrate and evaluate the modules developed for Pillar 1. One of the integration surfaces is the ROS software, is the ROS framework. Many of the modules have been integrated there, and basically the modules that would add a lot of risk in the experiments, such as having pedestrians in the scene or other vehicles. These are demonstrated in ROS, and also as an integration surface we use the software framework running on the real vehicle and the anti-hacking device, which is a device that has been contributed by T-Systems, a partner of ours in the Caramel project. Now I would like you to show you a live demo, what happens inside the car and how does the viewer perceives the autonomous functions and the mitigation of the attack performed in the sensors. So, as I have explained you, we have engaged a Mercedes C-Class for Caramel. The vehicle is equipped with a multiple variety of sensors, and due to the fact that in our IoT Congress we are not allowed to move the vehicle, we are only able to show you a subset of the functions that will be demonstrated in the final demo. And the functions that are going to be demonstrated here is the moving object detection while the sensor is being attacked by a cyber attack. So in the co-driver seat we have a screen which presents that the output of the sensing functions running in our computational unit. So as you can see, all the detected objects before and after the attack, the quality of the detection before and after the attack is not actually affected. And you can see that still the objects, we are able to detect all moving surrounding objects and the location of the objects, their coordinates in the 3D world, and also the direction of their motion.
In this simulation, we have created, well, in the backend, we have developed a controlled environment that allows us to represent what the backend does in the cloud. In this scenario, we have deployed plenty of vehicles that are sending GPS signals to the backend. So, and we can see here in this specific area that there are some vehicles with a signal being defaced from the original GPS signal. So this is considered an attack by the backend. So the more the vehicles that are in the same location, the more secure the backend will be that there is an attack in this specific area. So there are other regions that, for example, there are no red squares. This means that there is no attack in this specific region. However, if we see here, we might have the effect of an attacker trying to manipulate a specific region in the city. So this is a threat, and the backend has the capability to detect such a threat. So let's imagine we have an environment. There are plenty of vehicles, and in this region where the attacker is, we have the GPS signals are being modified, and we can see these red arrows. So as long as we are doing the scanning through the city, we can detect here that the vehicles are being attacked. So the backend detects this information, and it can send back the information to other vehicles in order to raise the awareness of the GPS spoofing attack in the city.
So let's explain the Pillar 2 of Caramel project. Pillar 2 of Caramel project deals with vehicular communications. So we have to have in mind that in the near future, vehicles will begin to communicate between them. They will transmit different kind of information. The simplest one would be to send the position, the speed, the direction of the car. So with this information, we can provide services like collision avoidance, or I can be aware of some roadworks in the road, things like that. In the next step, what we will do is to transmit the objects that our car has detected. The car, it has the Lidar, it has radars, it has cameras, and is able to detect objects. So this is a very valuable information for the cars that could be around my car that cannot see these objects. So we will have information about objects we will have information about objects detected by cars. And the third level of information, it will be a kind of coordinated maneuvers. Coordinated maneuvers, it means that, well, the cars, before doing something, before doing some maneuver, will coordinate between them. For instance, if I want to do one lane merging, when my car begins to approach the lane in which it will merge, it can send information, it can send orders to the previous car in order that this car accelerates a little bit, and the other car, the car that goes behind, that brakes a little bit. So they make enough space for me to get inserted. So all these messages require one communication technology. They need to be transmitted wirelessly. So there are different radio technologies. There is one radio technology, the oldest one, that is a variation of the Wi-Fi. There is a newer one that is one variation of the LTE. And then these were the old, let's say more or less old, but there are newer technologies like new radio V2X or other technologies that will be based in 5G or 6G. So the main problem that having all these technologies present is that I will have cars using one technology and other cars using other technologies. So my main problem would be how to communicate these cars with different technologies. So in Caramel, we have deployed one solution for that. We have built what we call one forwarder, that is one element in the infrastructure that simply acquires data from the cars in one technology and forwards that this message into another technology. We will show that a little bit later. And the second point in this pillar is about security. All these messages that we transmit need to be completely trustful. Okay, I need to sign these messages in order that could be trusted by everybody else, by all the other cars. So we need to implement one public key infrastructure, one network of servers that are able to provide digital certificates these digital certificates will be downloaded to the car, and this car will use these certificates to digitally sign these messages.
So, as Casademont said, the idea from the Pillar 2 in Caramel is to securize the end-to-end communication between vehicles. To do so, this security process needs to start from the vehicles. In this case, we have OBUs provided by Nextium, which implements electronic security, so nobody else can extract or switch any of the electrical components from one vehicle to another. And then from the OBUs, it goes through the roadside units. From the roadside units, the traffic flow can go between the LTE networks or 11P networks, going to the MEC server. Inside this MEC server, what we have is several modules that are able to forward traffic from LTE networks to 11P networks, and also handle and manage all the certificates and public key infrastructure provided by Atos to determine which vehicles are genuine or which vehicles are not genuine. For instance, one of the attacks that we can demonstrate here today is to execute a GPS DAC spoofing. In this scenario, one vehicle is supposed to inject a fake positioning for itself, so other vehicles can detect that this position is not genuine, and they are able to revocate their certificate. So for the rest of the infrastructure, this attackant vehicle is no longer available to send any CAN messages to the rest of the users on the road.